everybody, welcome back to another Tuesday's Tech Talk. This week we're going to be following up where we left off last week when we were talking about crossovers, and we were looking at a little KEF model that we used an example of. We're going to look at briefly the measured responses on a speaker that was sent to me this week from a new upstart company, and we're going to then finish by looking at this little studio monitor that we've designed, using it as an example of a speaker that was designed based on the drivers and the performance of the drivers, and maximizing those and working with those frequency response of the drivers so that we minimize the filter that's used. So let's go back now to the KEF speaker. We looked at last week the frequency response of the tweeter, and how because it's loaded into the concentric driver, how it had a rising response, and how we could not use textbook style filters with a speaker like that. We have to build something custom that takes into account that rising response and levels it off, and we have to, like any speaker, design it based on the acoustic output of the drivers. I then mentioned that we use an elliptical filter on the lower woofer, or in this case the coaxial woofer, and we had some questions about what an elliptical filter is. Well, I printed off a little diagram of an elliptical filter for you guys to take a look at so you can understand what that means. This is basically a variation of a fourth order filter. You see the inductor in the cap and the inductor in the cap. That's what we call an electrical fourth order. That is, if we omit this capacitor here. A fourth order electrical does not necessarily mean it's got a fourth order acoustic slope. We could stagger these values to create more of a gradual slope, or we could make stagger the values to where we're creating a steeper slope, but that would basically be a fourth order network. Then when we add this capacitor across this inductor here, what we're doing is we're creating a quicker shunt path to ground. We're letting the higher frequencies go straight through and back to ground, and it more abruptly cuts off the response. Again, we can stagger these values to change that slope a little bit. It's sometimes known as a 48 dB per octave slope. It's known often as an elliptical filter, but basically you just think of it as a really steep slope that it can create. In this case, I had to create a slope that matched the tweeter so that they both rolled into each other and made a smooth response. Here's the frequency response of the woofer, the tweeter, and the sum. You'll notice that it sums fairly smoothly. And then way down at the bottom, you notice a little green line that is be on this side for you looking at the measurement. That is the internal woofer that plays through the port, and it has a little bit of output that you can see in the response there. But yeah, it summed pretty smoothly, made a nice response, and you guys also wanted to know how the original frequency response looked compared to the new upgraded network. The original one you can see here in red. You can see that it has a little bit of a knee in the response at about 1200 Hertz or so, maybe 1300 Hertz. And if you look at just the raw frequency response of just that woofer by itself, you'll see that it also has that knee there. So what we're having to do with the filters, we're going to have to bring that level down and also create a smooth response. So it's a little bit tricky when you're dealing with drivers that have peaks and dips within the response. The dipped area was brought up by the inline capacitor at the front of the network that brought that level up a little bit and smoothed it out so that it made a fairly smooth frequency response. And then you guys asked to see a comparison. If you look there, here's the overlay of the two. The red line is the frequency response of the original crossover. You'll see, from about 1K to 2K Hertz, there's a brightness there. There's a heavier output there. It would be heard as a little bit of brightness or forwardness in that area. You'll see the green line is the new crossover design. You'll notice it's much smoother, has a more balanced response. I left it a little high at the very top end on axis, as you see there, so that when you're about 10 degrees off axis, it will be much smoother. It will be a flat response. And I mentioned too that an upstart company sent me a speaker this week. They sent me a mini monitor. I'm not going to say who it was or anything about the company, but it's a perfect example of what we're talking about right now, what I've been talking about, in that the drivers that were chosen were pretty top level drivers. They were nice, fairly expensive drivers. The cabinet design wasn't really engineered for them. It was a little wide. It created a lot of surface reflections. It had a crossover that was designed based on Harris Tech software, and what the Harris Tech software does is you input electrical parameters of the drivers and you tell it what order network you're wanting to use with it, and it'll calculate textbook values based on those electrical parameters. So when I measured the speaker, as you would imagine, the impedance response looked pretty good because it was designed based on electrical parameters. Unfortunately, it didn't take into account the surface reflections of the baffle. It didn't take into account the acoustic offset of the drivers. It didn't take into account the acoustic output of the drivers, which is what you need to know when you're designing a filter. So how did it look? How did the frequency response look when the filter was designed based on electrical parameters? Well, here's the frequency response. It's a red line. Notice it is really rough. There's a huge sucked out area in the response. The levels don't match. All of this because it was calculated. It wasn't designed based on measurements. And the vertical off axis looked even worse because as the microphone moved up higher, the acoustic offset of the drivers became further out of phase and it created even more of a dipped area. The horizontal off axis looked fairly smooth, but it also mirror imaged the horrible on axis response, so it looked bad. And if you look at the spectral decay, you'll notice that about 1300 hertz the woofer had a significant resonance. You can see it there in the spectral decay. It's ringing for a long time, and that's something that you would have to take into account when designing a network. You'd have to fix that stuff. Basically, the drivers just really weren't suited to be matched with each other in the application. So back to the drawing board. I'll help those guys get everything straightened out. But it's a perfect example of how you do not design a crossover based on electrical parameters. Now, here's one that's designed based on not just acoustic output, but the drivers were designed to have a really smooth output without the use of a heavily corrected filter. The woofers are a little M165NQ. It uses our high strength polymer frame. It uses a treated paper cone. It's a 44 millimeter voice coil. It's got copper shorting rings above and below the voice coil. It's got a solid aluminum phase plug, copper coated. The whole motor structure's copper coated. It has a unique push-pull motor structure that has a neodymium magnet on the pole piece. It has a ceramic magnet on the top plate. It produces a very smooth response. It doesn't have any breakup. It doesn't have any ringing. There's no frame ringing. It's easy to work with. The tweeter that we've mated it with is the GR Design Neo 3 tweeter, and it is in a waveguide. And the waveguide is 1.5 inches thick, and the reason it's 1.5 inches thick is it perfectly aligns the voice coil or the playing surface of the Neo tweeter with the voice coil of the woofer, so that it's perfectly in phase. The waveguide also lifts the output of the tweeter at the lower ranges, so the lower ranges are lifted up and maintained a flat response with the upper ranges, so it allows it to play really low, and we're not having to force it to play really low electrically. It just has an acoustic response that plays down really low. Crossover point is right at about 1400 hertz. If you want to look at the frequency response, here's the measured frequency response of each of the drivers. Notice, big advantage, the woofer's not having to play up very high, so immediately it's handing off to a driver that's extremely fast, has no stored energy, so the whole thing has a really smooth spectral decay. If you look at the spectral decay, you'll see really smooth, everything cascades down really quickly, no stored energy, so it's a very clean sounding speaker, very, very fast across the board. The little speaker is sold as a kit. It comes with the front baffle, all CNC cut. So all you have to do is put it together. Because we're not having to do anything fancy to correct the frequency response of the drivers. It's just 2 parts on the woofer, just second order on it only, second order on the tweeter, 2 parts only, and 2 resistors to level the output down to the woofer. And that's all it takes to get a smooth frequency response and to have a speaker that's extremely accurate. Also, something unique about this that's not ever been done before, the tweeter responds really well in an open baffle. It loves open baffle. Sounds really transparent in that application. So we incorporated that into a sealed box design. What we've got here is we've got a divider between the drivers that looks like this. It ramps up gradually to the back, and then the whole top is open. So there's just grill cloth on the back. There's no res on the sloped panel, so that some of that foam is absorbing a little bit of that rear wave information, but it's allowing some of that output to exit out across the top, allowing some of those spatial cues to be maintained within the room. So it's one of its primary purposes is using it as a studio monitor, and studio monitors typically are up against the wall or up against over a console, and there's very little depth there between the speakers and the wall. So usually you lose a lot of soundstage depth, or your spatial cues are somewhat truncated. This design gives those back to you. You're allowed to hear a lot of those spatial cues. You're able to hear a little better imaging, and a bit as if it was in a bigger room, even though it's not. So it's really ideal for mixing because it gives you a sense of space that you lose with a typical box speaker. It also has a resolution level and a detail level that is superb. You're going to hear things in the recording that you typically wouldn't hear from a typical studio monitor. So it's ideal in that application. You could also set it on a stand and use it in a room, well out into the room, use it with a sub, preferably one of our servo subs, and have a complete full range system. Again, the reason I want to talk to you about these and bring this up is it's a perfect example of something that's designed and engineered to have a smooth frequency response, so that we're not forcing it into doing something. We're not having to force it into a crossover range that the drivers aren't comfortable in. We're looking at smooth roll-offs and smooth transitions and less parts in the signal path. And typically, less is better. The more parts you put in the signal path, the more detractive it can be. So if you ever get an opportunity to hear these, you'll love it. I highly recommend it. It's a kit that we offer. The whole kit's $859. That's all the parts. That includes sonic caps, Mills resistors, ERCES high quality inductors, tube connectors, wiring, screws, solder, heat shrink, the drivers, the plans, the schematic, everything you need, including the front baffle that's already CNC cut. You just build the back half of the box as per plans, and you can have a really high-end, one of the highest quality mini monitors that we've ever done anything with, that we've ever measured or listened to anything. It is extremely high quality, and you can build it, and that's what we're here for, to kind of help support the DIY market and show you guys how to do this stuff and how to reach the highest levels of performance without spending a fortune to do it. You can do it. You don't have to spend the most money on the most expensive drivers. Money doesn't always equal performance. It goes back to the engineering of everything, whether it's engineered properly, how well the crossover is designed. And if you have questions about crossover design, again, drop them in the comments section. And if you have recommendations on episodes you want to see in the future for the coming weeks, drop them in the comments section. It may be a topic that I think is a great idea, and I'll use it. So again, thanks for watching, and we'll see you next week.